talk about the large-scale picture of the atmosphere where we've dealt with the globe. We've got down to the mid-latitudes. We've talked about extratropical lows and the difference there in cold fronts and warm fronts. Well, let's bring it down another level. I kind of showed you a hint at this past week when I put in the announcements about the thunderstorms and the rain moving across southeast Georgia. It was not connected with the front. Well, sometimes they can be connected with the front, sometimes they can't. But we're looking at a small scale. We're going to deal with thunderstorms. Thunderstorms can be very violent, or they can be, it rained a little bit, nice little lightning display. We're done. And there are a few showers and thunderstorms, convective in nature, that's going across Louisiana and all now. If you were to look at this is a high resolution current map of what's going on. What I want you to notice is in the blue, or the darker color, solid line, is what's called moisture convergence. If we're going to lift something into the atmosphere, we want to lift the air up to make it unstable, to make it condense. Well, we need convergence to do that. Well, when you combine that and add the term of moisture to that, we're basically getting a moisture advection convergence together. What that does is enhance thunderstorms. It's bringing moisture in, helping the condensation, helping to make it more unstable. There's some of that going on along this area of showers, especially southern Louisiana, very eastern corner of Texas there, a little bit more enhanced in that area. That is a section that you would expect thunderstorms to develop later. So this is a way to see if the thunderstorms are going to continue and to maybe see where they're going to grow more. It's not a lot in the way of cold fronts around this area right now. This is a line left over from a cold front to the west that's moved out ahead of that front and is actually dissipating some now. We're not expecting any severe weather out of this today or anything like that, but I thought it would be interesting to take a peek at moisture convergence with this line. Now, if you also want to know about stability, here's a term called CAPE, convective available potential energy. And the bigger the number, the more unstable the atmosphere. Notice it said potential energy. This is energy that is not tapped, may become tapped if the lift goes up enough, but it's not at this moment. Notice how extreme southern Louisiana is where you find it. The thunderstorms or the showers that are moving through Tennessee, northern part of Mississippi and all, don't have much to work with. But further south there's a better chance of it. So that is the area that they're going to be focusing on for more showers and thunderstorms. There may actually be some new development. You saw some moisture convergence in there. And the final thing that you want to look at with thunderstorms is wind shear. Wind shear actually helps to enhance the thunderstorm. So all you're looking for here is either change in direction or change in direction and speed with elevation. So if I was to look at wind shear with this, see if we can get one up here quick. This is what is termed as a 6-kilometer wind shear. Notice there's not a lot of wind shear along here, about 25, 35 knots of wind shear. To get severe weather, you're usually looking at 45, maybe 50 knots of wind. Anything over that, it gets much more interesting. So this is not an area of what we call potential. So let's go into what we're talking about. Well, how do these thunderstorms develop? Thunderstorms are a small-scale system. You can definitely look at these in terms of the pop-ups we get in the summertime, where you get a thunderstorm over your house and your next door neighbor get other showers around or whatever. I've watched these. They pop up all over my area sometimes, coming on the sea breeze where there's convergence from the wind with the sea breeze, lifting it. We've talked about that earlier. The thunderstorm goes up, it gets away from the sea breeze, it dies. So what you see here is the initial stage of a thunderstorm. The air is lifting up. All the air is rising in this air parcel. As rising, it condenses. As it condenses, it becomes unstable sometimes. In this case, it is. Eventually, it rises up enough that some of the air begins to come back down. Precipitation forms. And as that air sinks down now with the condensation side of where the cloud is, cools the air some. As that happens, the air sinks faster and hits out and spreads out across the ground. Eventually, all the air is basically sinking and none is going up. We have a dissipating thunderstorm. That is the classic example of how a thunderstorm develops, reaches its maturity where you have air going up and air going down, and ends where all the air is coming down. Now, thunderstorms do not necessarily stay in one little tiny cell like that. Here's kind of a categorization of thunderstorms. We have the single cell, we have multi-cell. Multi-cell means more than one thunderstorm, and they actually help to grow each other. We can get a squall line as well, which is multi-cell. Whole bunch of thunderstorms along a line. Supercells are very intense. They tend to maintain themselves for a long time, and they must have rotation. So here is a line of thunderstorms. Take a look at the one on the left-hand side here. New thunderstorms are developing on the bottom end of the line, propagating to the east. Notice that new thunderstorm here became here and eventually over here. What happened when it did that? It grew, became more intense until it was eventually the most intense, and eventually, however, it's going to dissipate. It'll become one of these cells up at the top. Notice the most strongest one here eventually is dissipating over here. So why, if these cells are moving to the northeast, is the actual line of thunderstorms moving to the east? Because the new cells are always forming on the bottom of this line, southern side generally. So that is something you'll notice with thunderstorms. You'll see them. The thunderstorms might tend to move to the northeast, but the actual line may be moving southeast. All because of where new cells or thunderstorms are forming. What do we need? We talked about it. I already showed you need a lot of maritime tropical moist air. To make that air go up, you need convergence of some type typically, and once the air gets lifted, begin to have condensation. The air heats where that condensation is occurring and winds up filling up and going up faster. So solar heating, especially in the summertime, drives it. There is a nocturnal jet that occurs out in the Mississippi, Missouri River valleys at night, which actually brings a maximum of thunderstorms there in the evening or overnight sometimes. And how many days of a year do we have a thunderstorm? So let's take a look at the map. Notice Florida. Wow. Greater than 100 days in the Sarasota, Tampa area. Almost a third of the year there's thunderstorms there. You ever think about it? 365 days, over 100 of those are thunderstorms. Almost on the average of every third day you're getting a thunderstorm there. Less than that when you go further north, obviously, until you get way up or out in California. But notice, even Alaska has thunderstorms. So these are all over. Notice how few are occurring in Hawaii. Hawaii is surrounded by tropical water. The water is warm. It's got mountains. Interesting. Why is that not getting them all? The reason Florida gets them is Florida has tropical water around it. It has two sea breezes, one on the east coast and one on the west coast. They converge, literally rising it up. Thunderstorms. And I used to live in Florida. the very first time I saw a thunderstorm there when I was just starting out at Florida State. I watched this thunderstorm develop to my east, and I had grown up in the Pennsylvania, northern latitudes. Everything went from west towards the east. I learned very quickly that I was on the southern height of that subtropical high. And instead of moving from west to east, they went from east to west, and I got soaked. So you learn climate. You got to understand where you are in relation to the large scale. Severe thunderstorms. I want you to look at this definition here. The definition is pretty straightforward. It says stronger than 58-mile-an-hour winds or hailstones equal to at least an inch or greater. That's all it says. There's no thing about lightning. We used to get a lot of phone calls at work when I worked for the Weather Service. Man, we got a lot of lightning out here. Yes, that's wonderful, and I don't want you to be out in it. But it is not a severe thunderstorm when it has a bunch of lightning. Severe thunderstorms are with the wind, which causes the damage, or hail, which causes damage. Now, as part of a severe thunderstorm, or part of a thunderstorm, you might get flash flooding, or even tornadoes. Vertical wind shear is needed to have a severe thunderstorm. First of all, it keeps the updraft mostly straight up and down. And secondly, it allows the warm, humid air to continue to pour into that thunderstorm, keeping it growing. If you don't have vertical wind shear, what you're going to wind up with is either the bottom cold air that's come down, sunk down with the rain shaft, is going to push out so far, it cuts off all the moisture into the storm. The storm's going to die. Happens many times. Or you're going to wind up more and more tilted with your top until eventually it doesn't work. Some of you are going to see a question this week. It's going to ask, what is the pattern, synoptic weather pattern for the Midwest, the southern Midwest? Basically, thunderstorm used to be Tornado Alley out here. What you have is a very strong upper level jet coming in from the southwest. You have a large meridional trough out there to the west. To the east of that, you're developing a ridge. So the upper level flow is from southwest to northeast. Now, you have low pressure up to the north over Nebraska, pulling air in. Remember, flow is counterclockwise around that low. So it's pulling air in off the Gulf of Mexico. What do you get? Very hot, humid air as your moisture source. And it's also from the south. We also get a low-level jet coming up off the Gulf of Mexico many times. That jet may run 50, 60-mile-an-hour winds or more. We have a high tropospheric jet running from the southwest that's running 100 miles an hour. Notice the wind shear. Every level almost has a different wind direction and tangent speed. So you have tremendous wind shear. You have the instability from the moisture. You got the cold air coming in aloft because you're bringing a trough in, so you're creating even more instability. All of that is what triggers these tornadic areas that develop out in the Midwest. Sometimes we got a stable layer, an inversion. If you're over Hawaii, we've talked about the trade wind inversion. This inversion here is going to be even thicker and wind up never being pushed through. That's why there are so few thunderstorms in Hawaii. Yes, clouds go up to that inversion. They may even get in a little bit of it. And it may rain a lot, but it is not going to thunderstorm. It's not going to get to the point where it reaches an altitude to cause thunder. These inversions can keep the air heating up at the ground, and if it gets hot enough, and instead of this being here, the temperature line went like this, then your air is going all the way up. You wind up with thunderstorms. So that would take until afternoon to do that. Lightning is a funny thing. Lightning is caused by graupel. Graupel is an ice crystal that has a little bit of water in it, a lot of ice in it, kind of a mix. And if the temperature is less than 5 degrees Fahrenheit, the droplet becomes negatively charged. Well, we know temperatures cool with height, so as these are lifted in the thunderstorm, charge becomes negative. Oh yeah, however, down at the bottom, where temperature is greater than 5 degrees, in the bottom of a thunderstorm, could well be very warm, maybe even 50, 60, 70 degrees. Those charges are all going to be positive. So what you've developed is a significant difference in charges between the top of the thunderstorm and the bottom, and that is why lightning develops. And with that, you get different, lightning works its way down. Another aspect of thunderstorms is the downdraft. Remember that air is coming down from the top of the thunderstorm, pushing the rain shaft down into the ground. If you're a pilot, one of the worst conditions you can ever encounter is a downburst on your flight path, that is when you're landing or taking off. The winds will change direction significantly, very strongly sometimes, with very strong winds, so that they have learned how dangerous this is. It's extremely difficult to correct from, and there has been in the past too many accidents with numerous deaths caused by this kind of thing. So most aircraft now are forbidden to fly around thunderstorms on the downdraft. There is radar, terminal Doppler radar, that is out there looking for these at the very lowest levels, trying to spot these downdrafts before they even can impact an aircraft. Because as soon as they're spotted, the aircraft are routed away from them. A derecho is basically a long area of damage. We had one in West Virginia a few years ago. I drove through it. I know what it felt like. I was driving into West Virginia in it. Other areas lived through it. Winds picked up were well over 58 miles an hour. Some areas got over 80 to 90 mile an hour winds. And that whole set of thunderstorms started to the west of Chicago. Developed severe weather there. They went all the way from Ohio, West Virginia, into Virginia, and did not dissipate until they moved off the Atlantic coast. I actually had damage when I went home at my house from these high winds, took down some of my trees in my yard. Well, that is one of the differences. A thunderstorm can cause severe weather by having these strong winds, but when they last for more than 240 miles and they're a straight line, we're not talking about tornadoes here, then they become a derecho. And you can see here how they form from an ordinary thunderstorm or two, combining together, and they may even become comma-shaped. Here is the classic one that occurred. You can see across, it literally started up by Chicago and went down to the southeast. Other ones went across up here as well. Flash flooding, think about it. All the moisture is getting pulled into these thunderstorms. Tremendous rainfall rates. We've talked about two ways that rain can form. And one of them is called by collision coalescence, means that the moisture is very high because the temperatures are relatively warm. And when that happens in a thunderstorm, the bottom part of the thunderstorm is very warm. The top's cold, but the bottom is warm. So you wind up with a lot of collision coalescence processes developing at the bottom of that thunderstorm. This can create tremendous rainfall rates and cause possibly major flash flooding. Big Thompson Canyon in Fort Collins, Colorado, another flood. I drove the Big Thompson Canyon about 10 years after, maybe 20 years after that flood occurred. I was out for a course learning about flash flooding. I actually knew somebody that died in that flood, and all they had to do was climb up 20 feet of rock that were on the sides of that canyon. But what they did instead was try to drive ahead of the floodwaters. They lost. The flood overtook them, crashed their vehicle into the creek, and drowned them. So be very careful. It doesn't take a lot of water to move a car. Hail is just frozen ice. Think about it. You've got a very strong updraft next to a very strong downdraft in the thunderstorm. Sometimes the water in that downdraft gets pulled back into the updraft, winds up freezing even more. till eventually it gets too heavy. And you can see hail shafts here. Hail shafts develop, and you are able to see them in dual pole radar, the newest version of the Doppler radar we have. And because of that, I can detect these in a thunderstorm with pretty good confidence that they're going to hit the ground. How big that hail is going to be, I may have some questions on, but I can tell you there's going to be hail. Tornadoes, they are violent, and yes, all these thunderstorms occur every year. Not that many actually develop tornadoes. Weak tornadoes are EF0s, EF1s, maybe less than 1 mile. They don't have a few minutes of a life. Violent tornadoes can go over 100 miles, be very wide, and yes, wind speeds over 300 miles an hour. There are two primary areas in the United States that has tornadoes. One is Tornado Alley, which runs basically from Texas to Nebraska. Another one's extreme southeast U.S., Mississippi, Alabama, maybe even into Florida. This is the average annual number of tornadoes by state. All right. I don't like this graph. I like this graph. This is the average annual tornadoes per 10,000 square miles. So now, instead of looking at a huge state like Texas, all the state, I'm looking at exactly the same area for each state. So notice, Kansas has the most tornadoes. Oklahoma, not far behind. Also, you have Iowa. Then you have Illinois. Both of those get a significant amount. And then down the southeast as well. So knowing the different aspects of this, and oh yeah, West Virginia does get tornadoes. As a matter of fact, I've worked some shifts where West Virginia's had 3 to 5 tornadoes on the ground at a time. Doesn't mean they happen often, and yes, the mountains can disrupt. Or I have seen tornadoes touch down on the top of the mountain, go from mountain to mountain, basically skipping across and not hitting the valley as well. So be aware that yes, they're not frequent in West Virginia, but they do occur. Here's one of the worst tornadoes ever, went through Joplin. It's caused a lot of trying to figure out, okay, how do we forecast a tornado? Tornado warnings were issued before this ever touched down, right out in here. It took 1 hour for the tornado to reach the east side of Joplin. That tornado warning was issued for 2 hours. However, people living on the east side of Joplin didn't know what to do because they assumed that the tornado was done, even though the warning was still up. They said it had been an hour since, well, the initial warning. They had taken shelter. They haven't seen anything. And some of them came back out, and they became victims when the tornado actually went through. So it's a great social science experiment. How long do you issue a tornado warning for? So I hope you got a little bit out of all this, and let me know if you have any questions this week.